Alrighty, class. So today's lesson was on 7.5 properties of trapezoids and kites. As the name would imply, we were going to be talking about those two different shapes. And if you haven't gotten the notes down, here are all the blanks. So trapezoid, parallel, bases, base angles, legs, isosceles trapezoid in that order. Okay, so you can take that some time and just put that down. And here we have example one. And example one says that ORST is a trapezoid. Okay. And one thing about trapezoids, though, is that we should know, is that, well, we first need to go back to this here. Trapezoids are very particular. Okay. Trapezoids have exactly one pair of parallel sides. Okay, that's how we'll define it. Just one pair of parallel sides. And so we call those the bases. But then the other two sides is what we call the legs. So the non-parallel sides are called the legs. So kind of just like the same legs that you would find in a hypotenuse triangle. Or sorry, a right triangle, rather, I should say. But if we have those legs to be congruent, we call it a trapezoid that is isosceles or isosceles trapezoid. It all works. Now, but something that is going to be helpful for us for this problem is that we actually don't need to confirm that this is a trapezoid because it tells us it's a trapezoid. And so we look at the problem and we say, well, it doesn't look like RS and OT are going to cross each other. And there's one of two ways that we can figure that out. One, we can figure out the slope, which is entirely possible, probably something that's a little bit better to do other than eyeball it. But the way that we know for sure that this is not going to intersect is, well, it already tells us it's a trapezoid. And the other two sides appear that they're going to intersect. So if you look at OR appears that it's going to intersect with ST, for example, here, if I were to extend those lines. But RS and OT, they don't look like they're going to cross each other at any point. So it tends to say that RS must be parallel to OT, which means that these are our bases. But because those are our bases, then the other two must be our legs. And so we have OR and ST, and these are our legs. And that's good to know, because in this problem, we're trying to confirm that this is an isosceles trapezoid. And so if we're trying to figure that out, we need to confirm if the two legs are going to be the exact same. And in order for us to do that, we must find the distance between those 2 points. So start with OR. OR is actually a lot easier than we may think. It's strictly vertical. So we're going to start at O. 1, 2, 3 spaces. OR is 3. ST, however, is not as simple. ST, we're actually going to have to use either the distance formula or Pythagorean theorem. But I'm actually going to use Pythagorean theorem. Okay. In class, I showed it the kind of shorthanded way, shortcut way, but I'll show the full way right here. So ST squared, which is our hypotenuse. And let's see, if I look at ST, and this is my triangle here, I have 1, 2 spaces, the 2 squares, one of my legs, and then 1, 2 again is another one of my legs. So A squared plus B squared equals C squared, or in this case, 2 squared plus 2 squared equals ST squared. And that's what we have. Well, this will then change into ST squared equals 4 plus 4, which is 8. And the only way to cancel out a power or a square is going to be taking the square root. And so what we're left with is ST equals the square root of 8. Now, looking at this visually, we could say, of course, that, well, 3 is not equal to the square root of 8. That doesn't even make any sense. It's not possible. So because they are not equal to each other, this is not an isosceles trapezoid. And you can say any number of things, but I'm just going to say OR is not equal to ST. Pretty simple. Do the same thing with extra example 1. My suggestion is you pause the video and you do it on your own first, see if you can catch it up or see if you can get the problem right or not. We'll move on. Again, it's telling us that we already know that this is a trapezoid. So we have to do a little bit less work, not necessarily no work, but we still have to do a little bit. We know this is a trapezoid, and let's identify our bases. It would appear that BC and AD to be our bases, because they are our bases, they're a trapezoid. These are parallel. Remember, these are our bases. And from here, well, it gets a little bit trickier. Really trickier, but we can still figure out what those legs are. And we have AB and CD as our bases. Or sorry, not our bases, our legs. I misspoke earlier, my bad. But these are our legs. And we'll do the exact same thing we did in example 1. We'll just solve for it. So AB squared equals, gotta make my right triangle. 1, 2, 3, 4 spaces. Then 1, 2, plus 2 spaces. Those are our legs, which then this changes to AB squared equals 20, because 16 or 4 times 2. Sorry, 4 squared is 16. 2 squared is 4. Add them up, we get 20. And so this therefore means that AB is equal to the square root of 20. Okay, we've done that part. Now we have CD. CD squared, well, gotta make that triangle again. 1, 2, 3, 4, 5, and then a 1. So we have a 5 squared plus a 1 squared, like so. 5 squared is 25. 1 squared is just 1. So CD squared equals 26, which of course doesn't make any sense because these two are not equal to each other. Therefore, not an isosceles trapezoid. Okay. I apologize. It really looks like a weird letter. But this could be a trapezoid. And of course, we can say the reasoning to be AB is not equal to CD. Something like that should be fine. Now we have key point 2. Key point 2 talks about specifically isosceles trapezoids, so definitely a note to make. Only for isosceles trapezoids. Okay. And so here we have these 3 new theorems, and some of them are a little bit easier to understand than others, and that's okay. But for 7.14 isosceles trapezoid base angles theorem, man, that's a mouthful. The thing you want to really pull from this one is that the base angles are congruent. That's all that it really says. Base angles are congruent. But I'm sure you're asking yourself, well, how do I know if it's a base angle? The best way I've seen it, or the best way I've been able to explain it, is that if it touches a base, then it belongs to that base. Okay. So in our example here, where BC is the base or a base for our trapezoid, angles B and angle C are both congruent. You see that right here? And the same is going to be true for AD. AD has these 2 angles, which means that those 2 angles are going to be congruent. Okay. That is the best way I've been able to figure out how to explain it. Then we have theorem 7.15, and it's actually the converse of the previous theorem we just looked at, where it basically says that if the base angles are congruent, then we can prove that the trapezoid is isosceles. Okay, so this one you can just use to prove to be isosceles. Trapezoid. I don't foresee a whole lot of proving to say something is an isosceles trapezoid, but you never know. It's entirely possible. Okay. And the last thing, the isosceles trapezoid diagonals theorem, these are going to be congruent. So diagonals are congruent. And that's it. Okay. Example 2, I think anybody could probably solve, even with the information that we know right now. Definitely we're going to have to use that 7.14 theorem. It's definitely going to be useful. I urge you to pause the video and try it on your own first, then come back to see if you got the right answer or if you're stuck. And so what I'm going to do, I'm going to first list out what I mean. Angle B, measurement angle C, and the measurement angle D. And the nice thing is that it already tells me it's an isosceles trapezoid, and it shows that I have tick marks and everything. I know measurement angle A is 42 degrees. I'm supposed to find those three angle measures. Remember, base angles are congruent, so angle A is going to be congruent with angle D. And same thing with B and C. So I already know that those parts are going to be congruent. So if I know angle A is 42, by transitive property, angle D is also 42. That one should have been super easy. Then the next thing here is, well, I know that this is a quadrilateral. It has the interior angle sum of 360 degrees. And I'm gonna just figure out what those other angles are. I already know B and C are congruent to each other, so whatever I get out of this, I'm just split in half. So I know 360 degrees lives inside of this trapezoid. I know 42 and I know 42. Let's subtract that. When I do that, I'm gonna get 276. And this is an important number because 276 is not our answer for either of these angles here, but it does give us those angles. And the way that we're going to get it is we're going to divide. Remember, if they are congruent, they are directly equal to each other. So I'm going to take 276 divided by 2. I'm going to get the answer of 138. So that therefore means that angle C and angle B 138 degrees. And that's it. That is pretty simple. Nothing too difficult about that. Key point 3, we talk about kites. Kites are a very interesting shape. The only way to define a kite is that we have two pairs of consecutive congruent sides, but more particularly the opposite sides. It's very, very odd. So two pairs of congruent consecutive sides. And something that we should also notice is that we have no parallel sides at all. I think a very important thing you should know about kites. We have no parallel sides. Whereas everything else we've talked about had at least one pair of parallel sides. This one has none. Zilch, nada. None. Okay. So we look at this and we're thinking, well, we have two more theorems. Good gosh, man, there's a lot of theorems in this one, and that's true. But there's some good stuff. This is the last theorem that we'll learn in unit 7. But of course, we do have a quiz coming up, and we have some exam coming up. So be happy all you want, but you got something else around the corner. Okay. And simply for 7.18, what we're going to put is that the diagonals are perpendicular, as you can see. We have the right angle there. AC and BD are diagonals, and they cross each other to make 90-degree angles. And so for 7.19, the kite opposite angles theorem, this is a very interesting kind of theorem to describe. And I find the most effective way to put it is that if we take AC, the diagonal AC, and we compare it to the diagonal of BD, we know for sure that AC is smaller than BD, at least in this picture. And so the way I would say it is shortest diagonal connects the congruent angles. That is one way to describe it. If that doesn't really resonate with you, or if you kind of don't feel like it doesn't work for every single time, well, the way that you could potentially describe it is a little bit weirder than how I've described it. But you could say angle in between the two different sides is congruent with the other angle in between the two different sides. Okay. And I was writing that, and it feels kind of counterintuitive to say. It makes sense, but now that I think about it, I think I could probably write it a little bit better. And if I were to change it, I would say the angles in between the two different sides are congruent. That's how I would change it. The angles in between the two different sides are congruent. So to kind of visually see what changes I would have made, angles in between the two different sides are. That's what I would do. Just change those couple words. So really, you don't need that bottom part. As long as you have this idea that angles in between the two different sides are congruent, you're perfectly fine that way. Look at example 3. Example 3 is not a hard example. And actually, example 3 and example 3 are very similar to example 2. Very similar. So we look at this, and we know that DE and EF are congruent, EG and GF are congruent. We can therefore conclude that this is a kite, even though it tells us that it is a kite. And we're only looking for the measurement of angle D. Well, from appearance, it looks like DF, the diagonal DF, is shorter than the diagonal EG. And that makes sense for us to say that D and F must be congruent to each other. So angle D must be congruent to angle F. But something else that could tell us this is one of two ways. Well, for one thing, we said before, there's a second way to put it, and that the angles in between the two consecutive sides or two different sides are congruent. So therefore saying D and F. But also, look, we already have E and G. If E and G are not congruent, we know kites are going to have one pair of congruent angles. Therefore, D and F must be our congruent angles. Okay. And we're going to do the exact thing we did beforehand. We're going to take 360 minus 115 minus 73, and we're going to find whatever that angle measure is, which appears to be 172. That looks like an A. 172. Because I know D and F are congruent, divide by 2 on both sides, I'm going to get 86 as my answer. Therefore, the measure of angle D, that's an ampersand, is 86. That's even worse. 80, oh my gosh. I don't know why I'm having so much issue with this. 86 degrees. Sorry, I don't know what that was all about. 86 degrees. Good. Try your example on your own. Then come back. Again, the same idea. We're going to have AC be our diagonal that connects our two smaller angles, or sorry, congruent angles. So I take 360 minus 80 minus 50. I'm going to get 230. Because I know C and A are going to be congruent to each other, then I just take 230 divided by 2. I get 115. Therefore, the measurement of C is equal to 115 degrees. Okay, so just to make sure that we have all that taken care of. And now here you want to be careful. Okay, we don't actually have a key point for, at least not in our notes, but it is something that we kind of, just like a section heading, that kind of thing. Example 4, what is the most specific name that we can give for this quadrilateral? This is where it gets really tricky. So you really need to have that flow chart. You really need to have that table ahead of you so that you can see and reference it. And this problem, it doesn't tell me anything about my actual side lengths. It tells me about diagonals, but not about my actual side lengths. It also only tells me about my diagonals. So I have to figure out, well, what diagonals look like those? It looks like BE and ED are bisected, like that segment BD is bisected. And it also looks like AC is bisected. And so the only thing that I could think of that's going to have confirmed bisected diagonals is going to be the parallelogram. Also, if you reference 7.6 theorem, it shows exactly to a T what kind of picture it is. And so this is what I was talking about in class yesterday and today, that we have to work with what is given to us, not by our assumptions and what it looks like. We have to be given something in order to make a conclusion. We can't just conclude something without having any reason for it. And so with example 4 is actually more difficult than we may think. Okay? Because it's so abnormal, it's so new. Sometimes we didn't even think about some of the new stuff we talked about. Here we have one congruent side, or rather one pair of congruent sides. Then we have one parallel sides. And you may be thinking to yourself, well, I don't know, right? I've only really seen parallelograms, and those have two congruent sides. Don't forget, trapezoids always have exactly one parallel side. So we know for sure this is going to be a trapezoid. Just knowing that we have one parallel side. But the kicker is that because we know we have the congruent side as well, and it's not on the same side or same sides of the parallel sides, then we know it's going to be an isosceles. Okay. This would have been different if I knew JM and KL were both parallel and congruent, then that would be a parallelogram. But because I know that they are on opposite sides, opposite pairs of sides, then I know for sure that this is going to be an isosceles trapezoid. Okay, so this is probably the shortest video I've made. Of course, if you have any questions, you can ask me at an appropriate time. Good luck. Make sure you're studying, and I will see you all later.